Yeah, actually, yeah. Thanks. Right, good afternoon. I hope you've been having a good couple of days. So my name's John Elliott, and for this part of the day, the rest of the day, we're going to be focusing on parts of the earthquakes. So it's using the Earth observation tools that you've seen, but to look at the earthquakes that occur on Earth and the deformation modeling approaches that we take. Then later this afternoon, we move on to a different part of the earthquake cycle, the intercycle. So what I'll do is I'll just lay out what we want to introduce to you. The earthquake host seismic deformation part, and we want to understand earthquakes so that we can improve our interpretations of faulting, the active faults that generate earthquakes, and the seismic cycle itself. And we will use elastic desiccation theory to model those to retrieve parameters we want to know about a fault, its orientation in space, how much it's moved. And the reason we want to do this is because the earthquakes tell us something about the growth of geological structures, fault propagation, folding, for instance. We want to look at fault slip rates through time, what we can measure today versus what the long-term geological rates are. So we can compare whether they're constant or time varying. And it enables us to look at the distribution of crustal deformation across the continents and look at, by measuring stuff at the surface, the nature of faulting at depth, we can make an inference about what's going on deeper down. We've got to look at, in earthquakes, the way that the faults segment and break up into different parts, and then how they might grow through time, so the time evolution of it. And then looking how it feeds into this earthquake cycle, this idea, if you have an earthquake, period of strain, build up, quiet, and then another earthquake over many hundreds of years, usually. And also we want to understand a bit about the deeper earth rheology, the stress and strain relationships we have deep down. Those surface observations can give us some idea on viscous processes of depth. So looking at the earthquake cycle then, here we've got Turkey, North Anatolian fault runs through the mountains here on the northern side with the Black Sea to the north. And if we look at two things, strain, evolution through time, and how fault slip evolves through time, the far-field block or plate motion builds up strain on a shear zone at depth. Which means, if you've got the lights, I'll just do the light. Should be the light now. How the interseismic strain builds up over time, the slip at the surface is zero. So this is pressure building up at depth. But when you overcome the fault strength or the friction, you get a sudden release of that strain in the coastline here that gives you slip at the surface, which is the rupture of the earthquake itself, something that you can then measure in the field, how much has offset the ground. Then in the hours, days, weeks afterwards, you get some post-seismic deformation. This may be after slip, so this is deeper slip on the fault plane extension, or it may be further field viscoelastic relaxation. Before you then return to the next part of the cycle, building up that strain over time, but without any slip on the fault. So that's our basic, very starting model. So that's useful in the short term to identify the hazard and maybe explore the time dependence in the earthquake cycle. And in the long term, looking at interplay between faults and the growth of topography, the distribution of strain, how you grow mountains and deform the continents. Now, one of the big important things about earthquakes is the potential for devastating impacts. They're a natural hazard and they lead to human disasters. So over time, looking at the types of disasters in the last 100 years, there's been a decrease in their impact on human populations across many of the different kinds of natural hazards. But earthquakes have been low but persistent contributors to that, so they now can often dominate the fatalities that occur from natural disasters. Now, the reason it's been quite difficult to tackle it as a hazard is that we're often surprised by where these earthquakes are. If we look at where cities are and where people live, there's a long recurrence between earthquakes. It's not on a human lifetime, it's much longer than that. So we're surprised exactly where they are. We need to apply our knowledge globally, studying different earthquakes, different places, and applying some of that, the physics of what happens to the local context. We can do this by interpreting the geomorphology as well. And these earthquakes, where they end up causing the hazard and the risk that results, you end up with fatalities of tens or hundreds of thousands of pounds, hundreds of thousands of people centered on these large cities, urban centers, as populations grow and densify into these urban centers in buildings that cannot be seismically resistant or aren't built to be seismically resistant. Now, one thing people have been trying to increasingly do in the last 10 years is to change the assessment approach, and instead of looking at where earthquakes happened in the past for informing where they may happen in the future, is to look at that build-up of pressure that leads to the earthquake, so the more causal side of it. And that's what we've been trying to do in the past, is to improve on that. So one particularly extreme example of this is Yushu in China, an earthquake I worked on many years ago using INSAR. This was the buildings as seen in optical satellite imagery before the earthquake, and then you can see the vulnerability, the fragility of those buildings means that there's been near total destruction in an earthquake that was relatively not large, less than magnitude 7, and it affected a large fraction of this city. Similarly, northeast China, where a lot of our research is focused across the Tibetan Plateau in China, you've got Beijing here, and you've got Tangshan here, and that was the site of probably one of the most deadly earthquakes in 1976, magnitude 7.5. But it's not actually possible to easily see the rupture across the North China plain there. But you've got this large city of Beijing that has built up. If you look at the satellite imagery, the urban extent of that has increased massively to the point where there's 22 million people sat very much on a whole network of faults beneath that region. So these are all drivers to try and improve our understanding of the deformation of the crust, where are these faults, and looking at the hazard. So why is it so difficult to predict earthquakes? Well, if we look at patterns, if we try and look at earthquakes over thousands of years, if they occurred very regularly, this would be a much easier job to do. If we knew they occurred at a regular recurrence interval every 100 years, then you would have ability to predict them in time. So that's an example here, but there's no variance in how often they happen. If they were normally distributed, at least you would have some guide that, the longer you wait, the more likely it is to occur. But if it's a Brownian distribution, then the time since the last earthquake is independent of when the next one will occur. And then sometimes there are some examples where earthquakes clustered, such as along the Dead Sea Fault potentially, where if you had an earthquake, it actually makes it more likely you're going to get another big earthquake. So the problem is we don't know enough of the time history of all these faults, because we haven't got records going back long enough to measure it, and we don't know really how the faults behave. Some of them behave a bit like this. The Alpine Fault in New Zealand does have a fairly tight distribution, and we know how long since the last earthquake is well recorded. And then other faults perhaps behave like this, or they're like it's best to model it as a Brownian failure model. So we just don't know which of these things, the underlying sort of pattern. So it's been a challenge to predict earthquakes. People have tried for many decades. So maybe it's better to forecast it and find ways to improve our assessment. So Earth observation in its form of SAR satellites that you're looking at, GPS satellites, can feed into various parts of the disaster risk management cycle. Today, we're looking at the earthquake part, what we call the co-seismic. But there is a response phase for satellites useful in the post-seismic, and a recovery period. But later on, when we look at the interseismic this afternoon, it's more about preparing, saying where that strain is building up and where you worry about it. So that's something we're doing here, continental strain wave fields from INSAR, so that you can actually inform decision making for the future. Now, it's been possible to do this because since the early days of just having a few radar satellites, it's exploded. We've actually now got lots of Sentinel-1C and D have been launched. NISAR's now been launched. This figure quickly gets out of date because there's been a huge flurry of availability of SAR satellites that have interferometric capability. So you can really do quite a lot, depending on how open the data is. The ESA Sentinel data is very open, but some of the others is a bit harder to get hold of. But it has been a bit more of a golden age to make these measurements. So what we have is we have these observations that we can make. The radar, often combining it with information from GPS if it's available, seismometry, so your seismic analysis, it can be all combined together to measure how the Earth performs in an earthquake. So that's our observation, our data info. Now from the data, we do some sort of modeling approach. This is trying to get at how much did the fault plane here slip at depth, high, low, where did it move, and where, more importantly, perhaps, did it not move in the earthquake? Because that's where maybe it would rupture in the future. And we can compare that with surface observations from field geologists measuring the offsets of the fault. But our reason to go from that data modeling approach is then to interpret it, to have some analysis of what's going on, how much of the mountain is growing, how much of the fault is growing, So understanding how it relates to topography, or how does it reorientate the stress on the fault network? Which areas have reduced in stress, the blue colours, where the rupture happened, and where that's pushed other faults nearer failure, the red colours, the surrounding faults. So, as I said early on with ERS and MSAT, the period from the 90s to 2013, it was possible only really to look at about 100 earthquakes. But in the last 10 years, there's been a massive explosion in the availability globally to measure onshore, continental, and subduction-related earthquakes. So there have been studies and compilations building on these observations, and a PhD student here at Leeds, John, who will be joining us later, has built a semi-automated way to process more and more of these. As we get more data, it gets harder and harder to do individual studies, and you have to do them en masse in an automated fashion. But the kind of numbers of earthquakes that we want to look at, each of these balls represents a different type of earthquake, varies by size. So there's only once every 4 years a magnitude 8 earthquake that you could measure with INSAR. So we're not often measuring the biggest earthquakes, but there are plenty, there's dozens or 100 almost earthquakes you could measure every year with INSAR. It can't measure all earthquakes, it's not a sensitive seismometry, so you can't get below magnitude 5, 5.5 typically. It has to be onshore deformation that you're measuring, so you can't do INSAR underwater, but there's still quite a lot of earthquakes we can get information about. And that detectability limit is representing these. How small can we go, its magnitude, and how deep can we go? So the further away the earthquake is from the surface, where the deformation we are measuring, the harder it is to detect. So if we're trying to detect 2.8 centimeters here, so that's about a fringe that you would see in an interferogram, we can only really see magnitude 6 is down to about 15 kilometers. And magnitude 5s have to be really shallow, and they are detectable if they're really shallow. Whereas if they're magnitude 7s, big earthquakes, you can see them deeper down. And we've got down to 110 kilometers for the magnitude 7.5. I think that was you have to do a lot of processing. The signal to noise is very poor, but you can do it. So you have to think, if I'm going to look at earthquakes, you can't look at them all. There's a certain band that you can look at. Across areas that have good coherence, so you're looking at areas that didn't have much vegetation, so this is an example from Iran. Shallow earthquakes that happen in folds, for instance, in an area, they produce deformation that's measurable at the surface that you can model really quite well and get down to magnitude sort of 5, as this study in the Zagros. So what we do here through the Comet Elix portal is serve the INSAR data for most events that occur onshore above 5.5. So you can go on this portal and then select the data, and it's a bit hit and miss how complete the data sets are, because it's not always possible to capture it all. But we've got a growing archive now of earthquakes that mean you don't have to spend as much time getting the data, you can spend more time doing the analysis. So here's an example that was actually on the advertisement for this event. It's an earthquake that happened on the border between Kyrgyzstan and China last year. It's a magnitude 7. So you can go on this event page and download the data and have a look at where the fault may have occurred, and if you were going to model the data, you can do that. Look at its relationships to topography, whatever analysis you want to do. So what are those pictures actually showing? They're sort of rainbow pictures of deformation, these wrapped fringes that you've been learning a bit about. If we take an example, just a toy example here, satellite, C-band radar, microwave images the ground. The ground has a displacement in an earthquake, you get an earthquake rupture, satellite returns back round, then you're basically just counting the contours for the amount of deformation that you're seeing. They're very spatial. A lot of deformation near the fault, because that's where it moves the most. And then in the far field, very little deformation to a point where you get 0. So that's the elastic response to the Earth, snapping like an elastic band. So if I take an example from Haiti, a major earthquake 15 years ago, that killed a large number of people in Port-au-Prince, what's important here is the radar imagery tells you where deformation has occurred and where it didn't. So it didn't actually occur beneath Port-au-Prince, but the seismic shaking caused all the building collapses and fatalities. It occurred outside. And what you're trying to do with these images is just measure how much deformation is occurring. And it's a counting exercise. This is your unwrapping step. It used to be done manually a long time ago, 20 years ago. It's now done automatically by unwrappers. But you're doing contour counting to measure how much motion has gone towards the satellite and away from the satellite. So a bit like GPS, how much does it go up, down, left, right, north, south, east, west, but this is along the line of sight. So that's one of the complexities with the radar that makes it a bit hard to interpret it. You're not got a satellite image looking straight down, you've not got a GPS that's measuring 3 components of deformation. It's a single line of sight, so there's an ambiguity. You've got your point on the ground here, X, that could have moved towards the satellite by 5.5 centimeters to give you 1 fringe. But that same deformation measured in the satellite imagery in the phase could have been just from pure vertical, but of a larger amount, or pure horizontal motion by a very large amount. There's that ambiguity, because all that motion is the same in the line of sight, these wave fronts that you're seeing here. So there's that ambiguity. So often it's better to have more than one look direction. When we say we want ascending and descending geometries, it's good we want to take more pictures of the event, the earthquake, because you get more information the more you look. So Sentinel 1 was a big change for us 10 years ago. It's really opened up our ability to measure this because it's fully open data, it acquires systematically, it's the workhorse of all our measurements. It's relatively moderate resolution, but it does strip map mode interferometry, and it produced great images. This was the Napa earthquake, the one that affected California, destroyed a lot of the vineyard storage in that area. But it was a great way of showcasing the potential we have to cover large areas with this data. So I think you've gone over this a bit. This is the typical acquisition mode for it. The sun synchronous satellite. It's C-bands, it's about 5.5 gigahertz. And we're mainly looking at the interferometric wide soft mode. So it measured 250 kilometers. So a large fraction, a decent fraction of the UK. So if I show you an example of the bursts that it acquires, here's a area of the high Himalayas in Nepal, Kathmandu down here in the south. The radar imaging takes it in 20-kilometer bursts on 3 different subsources. And all the processing is done behind the scenes is to basically work with this single look complex data, stitch it all together, and enable you to do interferometry. So you get all of those. This is a multi-look image just to make it visible. It's not the phase, but this is the area that you're seeing. I emphasize why it's a bit hard working with radar imagery is the mountains don't quite look right because you're looking at them at a slant angle. They're illuminated differently. The hill slopes facing satellite are foreshortened but brighter because they reflect a lot of the energy, and you can get a lot of shadowing in very high relief areas. But you can see cities down here, they are high returns of amplitude. You can see some snow-capped bits, lakes that are low amplitude return. So it looks roughly like a satellite image does. So if we then flip it, orientate it correctly, there's sort of geocoding steps you have. Here's the INSAR data for the differences between 2 images before the Gorka Nepal earthquake 2015 and after. So over here you've got some long wavelength noise, and over here you've got a large number of fringes that sort of aliasing. You almost start seeing them. The fringe rate gets a bit high to measure, but basically that means the earthquake was here. So the first order thing, that's where we got it. You have to do a lot of corrections with it and enhancements. This is enhanced spectral diversity where you have to shift some of the SLC data to really clean up some of those long wavelength artifacts. That's often all done behind the scenes now, or the orbits are good enough that you don't need to do it. But in the past, it required a lot of that refinement. So then if we look at image here now, flip, this is the coherence. Low coherence is where you get vegetation, high coherence is where you got stable ground. You also lose coherence where there's been strong shaking in this earthquake. And then that's the interferogram map. So that's where all the deformation happened, where the mountains went up and where they went down. You can rewrap it to 10 centimeters different interval when you're trying to convey easier contours to people. This might be all water related out here, the sort of deformation you get here. And this is all the uplift of the mountains from the earthquake. So often when you're presented with these unwrapped polar colored images that show you the total displacement, so you're not counting those fringes. So it showed about 1.5 meters of deformation towards the satellite here, so largely upwards, southwards, and then motion away in the north. And what's important from this is there's no sharp contrast in that data. It's really got a smooth deformation field that instantly tells you this is a buried fault source here. There are other different techniques though that you can do along with the phase displacement values. So you've got of the conventional INSAR, so these fringes. You can get range offsets when they're large displacements. You're actually tracking the individual pixels themselves. So there's the offset in the power. And you can do that in both range and azimuth. Or you can use other techniques as well, MIA, to get different bits of information from it. How much it's moved in the range direction, which is a bit like conventional INSAR, how much it's moved in roughly the north-south along track. So that's useful for earthquakes. It's used a lot in glaciers as well. And it can be good at picking out the actual faults themselves. This example works on New Zealand. You basically work out where there's a sharp gradient, that's probably where the fault reached the surface, because either side of the fault, the cross moves in opposite direction. So we were able to pick out this fault here. There's a left lateral strikes at fault to the north of the main rupture. So it just helps you tease apart the different segments that have occurred in the earthquake. So if you look at plenty of these over time, you get your eye in for what these patterns are showing you. So you'll do an exercise later where you need to sort of work with these, and it takes sort of years to get quite an intuitive feel of what they are. This is a typical pattern from a strike slip earthquake that's orientated east-west or north-south. You get these sort of four lobes of deformation. Again, it's because of different contributions of up, down, north, south, and east, west motion to that line of sight. It's not just an easy map of east, west. Okay, we've got some exercise where it shows you what the east, west would be, but you've got to always imagine those three components of motion have to be converted into the line of sight. So they're not immediately interpretable until you've seen a few of it. But you've got a lobe on one side, a lot of fringes here. There's a lot of deformation in what you call the hanging wall. This is a thrust fault, not much in a footwall. This is an example from Iran. Similarly, these two are strikes of earthquakes, they're east-west orientated. And most of the motion then is from that horizontal east-west, and that's the simplest to sort of view. So, as I said, the important thing is that line of sight. So here's an example again of a DM, the height map, shaded relief from the Zagros in Iran. So where do people think the earthquake is? No colour bar, no, but from the patterns, where do you think it is? That dot there. Okay, that deformation. So the earthquake is smooth, so it's a buried rupture at depth, but there's 3 centimeters of motion down and 8 centimeters towards the satellite. So range change is decreasing there. So this pattern is easy to pick out. This one less so, because it's mixed in with the noise. The long wavelength noise actually comes from the atmosphere. This is all the difference in the atmospheres on the first image and the second image. Okay, the atmosphere changes. You can see rolls here that are to do with the convection cells and by hot areas. They're interfering because there are different patterns at 90 degrees to each other, probably on the 2 different acquisition dates. So it's hidden in there. But the important bit you need, as well as the line of sight displacement data, is something about the incidence angle. Because it's quite a wide swath now, the angle of incidence varies quite a lot. So in the near range, it's a bit more sensitive to the up-down than the east-west. And in the far range, it's equally sensitive to either. So you need that incidence angle information. And then at lowish latitudes, even actually quite up to high latitudes, it's a polar orbiting satellite, but even at high latitudes, the azimuth doesn't vary much. It's almost going north-south. But because it's traveling north-south, this is ascending, it's looking largely east-west. That's why it can see east-west. It can't see north-south. So there's always a limitation with that. So as I said, what we want is to have different looks on that. If you can imagine different satellite systems, and NISAR now its launch does look different in a different direction from Sentinel, it enables us to have that diverse range of bits of information that we can use on modeling, then get at the X component, the Y component, and the Y component. There's different contributions to it. So it resolves some of the ambiguity in that displacement. So you usually want more than just the descending. You want the ascending and descending if you can. More data is better. So the types of earthquakes, it depends if you've done geology, whether you've come across this before, but types of earthquakes we're going to introduce you to later. There are 3. First is strike slip, where you've got horizontal motion. So that's big transform faults like the San Andreas, the North Anatolian fault. It's those that are in the oceans offsetting the beach balls. This representation is that way that, say, seismology would see the the pattern of radiation from that fault rupture. But this one's akin to right lateral. This means motion on an east-west fault. So we can use that to work out the style of rupture in these events. You get normal ones if you're pulling apart the crust, maybe at the ridges, mid-ocean ridge spreading, or in normal faulting areas where the topography is so high that the crust is falling down as such. Then that extension needs normal faulting, dip slip. And so you tend to measure lots of fringes in the hanging wall where there's been large amount of vertical motion down. So that's largely vertical. Similarly with reverse faulting, classics are the subduction zones, but also continental collision zones, where you're doing faults and folding, you're forcing and shortening the crust. That leads to, again, a lot more vertical, but you get more uplift than substance. So you've got those three basic types of faulting you're trying to do. Now, on the oceans, they're very delineated along the edges of the plates, traditional plate tectonic theory. In the continents, note that it's much more distributed. So again, going back to that hazard and why there's so much risk, we live on the continents, and the earthquakes don't line up in nice straight lines the way they do in the ocean. So you can work out where the hazard was in the oceans. In the intraplate areas, it's very low. But on the continents, particularly across the Alpine Himalayan belt, because of the shortening of Africa, Arabia, and India with Eurasia over millions of years, you've got really quite a broad band of deformation. Means the earthquakes are broadly distributed, which means the hazard is broadly distributed. So it's much harder to work out where it should be. So one way we try and understand these, apart from the visual interpretation of the INSAR image, by looking at it, getting used to it, is to actually take profiles across the data and look at how much the ground moves towards and away from the satellite. So this is your elastic band sort of snapping. In the far field, it's doing nothing, and then it's a big offset at the rupture. So this would have been a horizontal. So this is the earthquake. This one's a large amount of substance due to the normal faulting earthquake I told you, so mainly down. Plus faulting, elastic response to this is mainly up. So you get an asymmetry in it. This is more symmetrical if it's strike slip, but for these dip slip, there's quite an asymmetry in what happens in the hanging wall versus the footwall. And often what we're trying to get from this is information about the orientation of fault in space, as I said, but also their size, comparing at the moment. So you can do that from seismometry, and you can do it from the INSAR as well. So one way we measure that, and you'll be doing these numbers, is the Newton meter. So that's how much energy there is in the earthquake, it's sort of potency. Then how big an area does it rupture? And it's rigid, how rigid it is, because that contributes then to how much energy it releases. So very basic things of length and width. If we just assume it's a rectangular saw, you can make it more complicated than that, but say it's a rectangle, dislocation is offset by U amount of meters. So we just want to be able to get those parameters to start with. The area of the fault plane, how much it's slipped, how rigid it is, and that gives you that moment, how much energy is released in it. So it's a 4 times the distance kind of thing you would have done in physics. So we also can use some back of the envelope things to make it a bit simpler and say, big earthquakes tend to slip a long way. Small rupture areas can only slip a little bit. So that's a scaling relationship. So that tends to be about that kind of ratio. It varies, it's sciences, so it easily varies by an order of magnitude. But you can then simplify it and say small earthquakes square, large earthquakes, they can't get any thicker, they can't get any wider than the seismogenic thickness, the bit that's able to support earthquakes. So that's 15 kilometers. So you can make these simplifying assumptions when you do this. And then to convert it to the sort of moment of magnitude of things that you sort of hear in the news, or it's a seismological calculation, you then take the log of that large energy value, then put it on a logarithmic scale, the MW scale. So when we look at faults in the field, this is an example from Greece. The various parameters you get about it is stripe, which is orientation in space, how it dips, the break angle. There are different things we want to understand about the earthquake that tells us about this particular rupture. So these are the sort of first sort of parameters you're after. Strike slip faults tend to be quite vertical, so they have a high dip angle. They have a certain rate that's 0 to 180. Dip slip faults tend to be more like 45 degrees, could be 30, 60, but they have a shallower angle. So you want to measure, like with the compass, the strike, the direction the fault's pointing in, its dip, how steep it is, and the rate, the angle of one hanging wall with respect to the footwall, so which direction is it slipping. So there are various things. If you've done this before, this is straightforward. If you haven't, it's not quite so intuitive, because the rate is the angle around from the strike direction that you're measuring. So if it's thrust like that, it's plus 90. If it's strike tip, it's 0, 180. So these are the sort of things we're trying to do. And we can compare that then to what seismologists see. So we can tell you the extent of the fault rupture with INSAR, but we can't tell you where the fault rupture started. So the hypercenter, where the point of slip initiated on fault plane, where did it start? That's something that seismology will tell you, but the INSAR won't. So epicenter is where that rupture started from on Earth. So you'll often hear the epicenter. We can tell you about centric depth, roughly how deep did this moment energy get released, but we can't tell you the slip history on the earthquake, just the total amount of slip, but not how it evolved through time. So we can compare the INSAR moment with the seismic moment, but there are some caveats to do that. The satellite INSAR observations happen usually days after the earthquake. And as I said, there was that post-seismic effect in the hours, days, and weeks after an earthquake that can give you extra moment release seismically. So you wouldn't always expect them to match exactly. So this long-standing elastic theory in a Karman model that's used to model fault slips as rectangular dislocations in the half space. And these are the main parameters you ask: the fault depth, length, width, dip. There's how much it's moved in the strike slip and dip slip direction. And if you're modeling volcanic systems, which you might do tomorrow, there's also you can have a tensile component as well. But we're trying to measure where is this fault plane in space. So there's also XY parameters of where it is. Now, before you can move on to the modeling bits, though, you need to work with your data. And INSAR is actually quite relatively high resolution, involves a lot of points. So you usually have to downsample your data. If you're going to do any modeling, you usually want to simplify your data. So often we would work with thousands of data points to model it. This is an example of the strike slip earthquake in Tajikistan, and you can see the blockiness. You don't need much data in the far field when nothing's happened, but you want more data in the near field where a lot's going on, where the slip is many meters. So you can find different ways of subsampling. Uniform sampling here, quad tree sampling, nested uniform here where it's high, medium, and low. There are lots of different ways of doing it and different reasons to do it, as well as resolution-based sampling as well. And then using that dislocation theory, you can model it. This is uniform slips. So those rectangle faults here have each moved a certain amount, about a couple of meters. And you can get that segmentation. So you can see which bits of the fault have moved a lot, and then where in your model you'd say, well, there might be a fault there, but it's not moved a lot. And whenever you do this modeling exercise, you've got your data, got your model, you look at the difference to see where there's a mismatch. So that's your residual here, and you're trying to get this residual down to the sort of noise of your data. You don't want to over model it, you don't want to do overfitting, but you want to capture the large scale features. So you can see there's a bit of a systematic residual here that's not being properly captured. There's a systematic green space, they've under modeled, half a meter of deformation. That means you could tweak the model depending on your approach. When you set up, there's a lot of choices. It's not very objective to do much of this modeling. You need to make some decisions. When you're doing this, it's setting up your fault plane solutions. You've got to pick the segments that are going to happen. So often we would use other data sets like the aftershock clouds here. This is for the Darfield earthquake in New Zealand and the Christchurch that happened 6 months later. You can sort of start joining the dots with the aftershocks. If they're really well located, they should lie more on planes they do. It depends what region of the globe you're working in, but you can start to pick out a pattern in these. So aftershocks tell you that, the seismology tells you stuff, and the INSAR tells you as well. One of the things that happens in near field with ruptures is we lose the INSAR coherence. The ground moves too much or it's shaken too much. So you can actually see there's a band here where it's not possible to recover coherent data. And that actually lines up pretty well with where you put the fault segmentation. So you've got a reverse fault out here, but you've got the main strike slip segments here. And then, as I said, there was that other data set, the azimuth offset, that meant even though we couldn't really see it in the conventional phase, you can just about make it out there. It's very obvious in that other data set, the azimuth offset, we can put a segment to there. So you build up that, you say, well, that's where I want to model it. And similarly for the Christchurch earthquake, it was a bit harder to work that out, but you would put the fault segments over there. You're trying to test where did the fault move and where didn't it move. In this case, the important thing was what was going on in here. There were some aftershocks, but we don't see any deformation. So what's happened to the stresses in that area? One of the important questions was, are there fault structures in there that could rupture in future earthquakes. So again, joining up the segments, this is where you'd expect potentially a future rupture to happen. Also, we want to look not just a long strike at the way faults break up into different segments, we can look at how they do at depth. So here's an example of a deep earthquake in the Chadam Basin, very smooth, long wavelength signal. And an earthquake that happened about a year later, exactly the same magnitude, the same place, but it's got a lot more fringes. So it's the same size earthquake, but it's got a lot more surface deformation. It must have been near the surface. So what I'm trying to address here was what's the relationship between the deeper one and its orientation and the shallower one, and why didn't it rupture through all in one go? And then in this Van earthquake, a lot of people in eastern Turkey near the Iranian border. This one was a smooth deformation field. You see the fault segments here. There was modelling around Lake Van, and all the rupture was really quite deep, below 10 kilometres. So it hadn't made it all the way to the surface. So what you would be worried about is what's going to happen on the up-dip projection of this fault plane in the intervening years. Because this bit broke, this bit hasn't, but you would expect this bit of the crust to eventually snap. And obviously being shallower and nearer the city, you would have a much greater impact than the deeper one did in 2011. So what you're doing in practicals is get your eye in what these inside fringes look like for, in this case, a shallow dipset fault, where you get a large amplitude asymmetric signal of a narrow width. But as that fault plane gets deeper and deeper, you can see it spreads out the deformation, gets a bit smoother. When it gets near the surface, those fringes tighten up, and if it actually got to the surface, you get discontinuity in those. And then you know where the fault plane is if you get that discontinuity. So you want to sort of, when you do some of the forward modeling, when you test this in your notebooks, you want to be playing with these parameters, get a feel for how deep is this. But remember, the kind of depths we're talking about in the continental crust where you can have rupture is about 20 kilometers. So some of the things you may want to look at are really near surface processes, 100 meters. These are really quite deep processes, but they're not deep Earth 1,000 kilometer processes either. We can't see that deep. It's that sort of depth that we're looking at, tens of kilometers. So have a look at the depth extent of faulting, the amplitude, total displacement you see, the wavelength over which is happening when it's narrow or wide, and the gradient you get from it. That gradient, that displacement, which is then the fringe spacing. Another aspect when you move on from treating it as a uniform dislocation, just a rectangle, to busting it up into really quite more complicated faults, is you've got to regularize the problem. So in this case, that means when you're doing a model, there is a solution that fits the data better, that has a very high amount of slip on it, unrealistic amount. There's many tens of meters of slip in one place and then nothing everywhere else. So that tends to be what happens with these inverse problems. So you have to apply a smoothing operator to the result. And that again is quite a subjective choice, how much you smooth it. You're trading off a more realistic amount of slip, not tens of meters, but a meter, spread over something that looks a bit more like a rectangle that you might, or an oval that you might expect a fault plane slip to occur on. And it's a sort of compromise. And if you've got surface observations of the amount of slip, you might have some independent constraints on it. Or if you have seismological solutions, you could try and constrain it that way. You can also look at your depth resolution, because often in fields like this, you look at checkerboard tests, because basically what it means is you're measuring deformation on surface. It means you can't infer very well, or you can't resolve very well what's going on at depth. So it gets blurry the deeper you go. So one way to show that is in checkerboard tests. You put in a known amount of slip into your model and invert for it, and you get back this. So it only recovers the pattern very well at short wavelengths in the shallowest part. Whereas if you're looking at big patches, 9 kilometer size fault segments, you resolve that very well shallowly and actually quite well deep, though it can vary depending where your data is, whether you do it very well. So those are checkerboard tests as well. So don't overinterpret deep patterns of slip at depth, because it's really quite a blurry picture. So if I show you an example from the Zagros that I showed earlier, this is, I think it was radar stat imagery over this event. This is the Zagros Mountains, southwest Iran. You get deformation in the hanging wall here. A lot of incoherence from this part. Iran's generally very coherent, but this bit wasn't quite so much. And what we get from that deformation is this slip at depth. So it happened between 5 and 10 kilometers on the first fault patch, but then it sort of stopped at a certain horizon, and then it jumped up to a shallower depth in the southeast. So basically, content marginalized the slip into two different layers. So if you then relate that to what's known about the geology in the area and the different formations, it seems that it basically has to rupture in between the salt layers where it can't propagate through and some of the shale horizons. So it will run along those. They actually act to compartmentalize the depth extent of rupture. So what you always want to do is bring in other observations, other independent measure these things to help you interpret what the INSAR is trying to show you to understand the fault unfolding. So as I said, what you'll be doing is the forward problem where you take this Akada source model and you say, given strike dip rate, length, width, what deformation do I expect to surface? But there are these inverse modeling tools. There's, it's a lot slower doing that, but it's the case of given the observations, what is the model I expect to get for that? And that's what some of these bits of software that have been developed by colleagues here at Leeds. One of them is called GBIS. So this is a Bayesian approach to doing that geodetic inversion. But given deformation, the data vector here, what do you expect the model to be based on how noisy that data is? So that's the Bayesian component, giving you a priors about what you think the fault parameters should be, how noisy is your data, so then you can get some idea of the uncertainties in the modeling. Also, if you want to then move from just simple sources to distributed sources, this is another piece of code here, Slippery, which will then do that regularization, that smoothing. There's a spatial smoothing operator called the Laplacian that makes it smooth like that. And there's perhaps a more physically realistic von Karman method that works on fractal analysis that does like that. So there are different choices that you can make about it, but they will do finite fault patterns. So depending on how much you want to go into the fault slip, you can use that. So in summary, we've got INSAR observations are a useful complement to other data sets, GNSS and particularly seismology, when the deformation is onshore, for getting at the location of earthquakes quite precisely. If you're looking at small earthquakes like John is, they can pinpoint it really quite accurately compared to some seismological techniques in places that don't have a lot of seismometers. We're getting an increasing large catalogue so that we can do a bit more statistical analysis on earthquakes within INSAR. And we can do that for the large shallow earthquakes. Not magnitude 3s, but we can do it for magnitude 5.5 and above. And each of those has helped contribute to our understanding of the earthquake cycle, how the fault segments release the strain that's been built up in long term. And I'll show you measurements we make of that long term build up of strain later. But then what we're trying to do is relate where that slip occurs at depth compared to lithologies and how it relates to the topography of the surface, where we're seeing it grow. But it's keeping in mind the limitations of this. It doesn't work underwater, and it's a surface observation. So there's limited resolution. The deeper you go, the less well you know it. There's an ambiguity in that line of sight, so you always want as many look directions as you can. And there are some modeling codes here with the GitHub links that you can do if you wanted to actually take that INSAR data from the earthquake catalog and model it to find out about the slip at depth. So that's the end of the lecture component. What we'll do next is the practical class, but I think we'll have a break for a bit. So are there any quick questions now before we start that? Yes.
About incidents.
Yes.
Usually, if I'm not mistaken, airfield is sensitive to east-west, and backfield is sensitive to up-down.
And it's the other way around. It's equally sensitive to east-west and up-down in the far field, and then in the near field, it's a bit more sensitive to the up-down because it's looking more downwards in the near field.
Can you explain to me why it is? What is the reason behind this?
Because your SAR antenna is at 700 kilometers up above the Earth. So when it's looking and emitting the microwave radiation out, the angle which it hits the Earth, the incidence angle, is a lot steeper for the Earth below you and a lot shallower in the far range.
Yeah.
Okay, so should we just break for 9 minutes and then I'm going to go find John to help with the next aspect, but that's going to be on the cosine bit forward modeling tool, and we'll show you some examples from that.
Recording.
Yeah. Yeah.